centuries, mathematicians have explored how to cram spheres into containers as efficiently as possible, but a promising new solution was recently published for all dimensions. Sphere packing, like many mathematical concepts, is helpful for some potentially obvious reasons, like engineering, as well as other potentially unexpected ones, like long-range communication and cryptography. In the 17th century, astronomer Johannes Kepler theorized the most space-efficient third-dimensional packing pattern, filling about 74% of space. A hexagon of spheres around a central sphere, which is actually the most efficient two-dimensional circle packing pattern, and then a triangle of spheres and holes up top. This may seem like a natural and intuitive solution, and you've likely encountered it before, like with fruit stacked in a grocery store. Although, to be fair, for problems in the real world, sometimes people think outside the box, like by making more storage-efficient cubic watermelons. But even if sphere packing in the third dimension, ours, was spatially optimized, why should mathematicians stop there? But before we can really understand high-dimensional sphere packing, let's go over the basics of shape organization. A spatial pattern or arrangement of points is called a lattice, which you might recognize from outside pure mathematics, like crystal structures in chemistry. To start sphere packing, you can simply take a lattice and make spheres around each point. Earlier this year, a mathematician, Boaz Klotag, derived an old method for sphere packing by Claude Rogers, where you could use any lattice as long as you had the right ellipsoid. An ellipsoid is a stretched or squished sphere, so it has differently sized axes, whereas the spheres are all the same. Rogers' strategy involved using a bunch of certain shaped ellipsoids on any lattice, and then squishing or stretching the whole picture until the ellipsoids became spheres. While many mathematicians turned toward different methods after a while, Klotag revisited Rogers using new ellipsoids he found, and ultimately got a far more efficient way of packing spheres than did most previous strategies, which relied more on symmetry and highly ordered lattice structures. But how do you figure out the volume of these ellipsoids, and by proxy, whether they would offer more space-efficient sphere packing? Well, first, let's see how it works for easier shapes, spheres, whose volumes you have to understand for any approach to sphere packing. You might be familiar with the sphere volume formula, 4/3 pi times the radius r cubed, and the circle volume formula, pi times r squared. If you squish the circle down to one dimension, line, we're just left with 2r. You might start noticing a couple of patterns already. The power of the radius increases by 1 each dimension, but the power of pi also increases by 1 after 2. The pi term is actually changing by 1/2 every dimension, and the reason we don't ever see the square root of pi is that the other part of the term, like where we get the 4/3 for spheres, is cancelling it out. Every 2 dimensions, this denominator term might also seem to increase with a single step, going from 1 factorial to 2 factorial to 3 factorial, and so on. But what's actually going on is called the gamma function, which for here can be defined as the integral from 0 to infinity of t to the z minus 1 times e to the negative t dt. This exhibits the same pattern as factorials with integers, but unlike factorials you might be used to, this function can work just as well with non-integer inputs. For numbers with a half, the gamma function outputs something involving a square root of pi, cancelling out the extra root pi from the pi exponent mentioned before in the numerator. And that's all the sphere volume formula is for any dimension: the radius exponent, the pi exponent, and an output from the gamma function. Now that we've gone over that, let's return to ellipsoids, actually a pretty easy mathematical jump. The concepts of volume with the coefficient, with pi and the gamma function, don't have any reason to change. All you have to do now is take the radius term, which is just an exponent for the sphere, since all of our sphere's axes are the same, with the product of the different axes of the ellipsoid. And now we can understand whether an ellipsoid will offer, in Rogers' method, more space-efficient sphere packing. This research is a great example of how people in STEM fields are discovering amazing things, and NSTEM works to empower that expertise, and future generations will push us even further in math and consequently other fields too, like long-range communication and cryptography. Contribute to this mission by starting an NSTEM chapter at your school, or becoming an individual global member today.